Welcome to the lecture on Fundamentals of Software Engineering Processes. In this lecture, we will explain what software engineering processes are and go over the principles and best practices in designing such processes. Think of this lecture as being part one of a two-part series. The second part will present examples that will illustrate the concepts presented in this first part. Let's start by tying this lecture to what came before. The earlier lectures described how enterprises compete and operate, and by showing how information technology can help by applying technology in a manner aligned with the enterprise. For example, by creating targeted applications that improve specific areas of an enterprise's value chain. An important additional aspect of alignment is the process that the IT organization follows in applying technology to the business. So we now look at what processes are and what alignment means with respect to processes. We expect students studying this module to come away with the following learning outcomes. First, an understanding of what software processes are and what benefits they might bring to the development of software. Second, an understanding of the best practices and principles that should be made part of a software engineering process. And thirdly, a sense of an understanding of how to customize processes to projects. The last item is in fact the most important learning outcome of this lecture.
What you talking about? What you talking about? What you talking about? What you talking about?
So why do we need processes in software engineering in the first place, especially noting that processes by themselves don't create value and in fact increase cost? We need processes in software engineering for the same reason we need processes in doing anything complex. We need them in order to predictably meet customer or stakeholder expectations, or more correctly, to reduce the risk of not meeting them, not meeting expectations, that is. Essentially, a process serves as a structure for software development. It helps achieve, firstly, repeatability. A software process becomes a recipe that you can repeat. Prediction. By repeating the same process, you can get better at predicting how and when specific tasks will be completed and when the overall software will be developed. Third, quality through standardization. By standardizing the process, you can make the quality of the product, which is the software application, more likely. Fourthly, continuous targeted improvement. You can identify which components are not doing so well and improve them, and improve them, and improve them, and improve them. Next, you can accomplish training. You can train new folks on a process if it has been well defined. You can use a process as the basis for their training. Next, traceability. You know what a step in the process is responsible for. You therefore also know where each software artifact came from. Hence, by recording process steps, you achieve what is known as traceability. Incidentally, there are human effects as well. For example, confidence building. A process that works well builds confidence in the team. The textbook definition of a software engineering process is a well-designed set of partially ordered steps intended to reach a goal. In software engineering, the goal is to build a software product or enhance an existing one. In my opinion, this is a mostly useless definition. It kind of reminds me of the story in which an explorer lost in the Arctic asked an Eskimo, "Where am I?" And the Eskimo said, well, he was probably a university professor in disguise. The Eskimo answered, "You are on a sled." However, it does serve to point out that a process has steps that are concurrent and that a process has a goal, which in software engineering is either to build a new software system or enhance an existing one. Here is a more useful definition. A software engineering process is a systematically designed method of developing and maintaining a software system through its life cycle. Note the emphasis on designed. Rarely are the processes the same across companies or even projects. Software engineering processes must be customized to the situation in order to be effective. So, how do we design a software process? We start by understanding software lifecycle phases, software lifecycle stages, the characteristics of software projects, the best practices in software processes, and then the best practices within each of the software development phases. By the way, we'll do this last thing in the later lectures, not in this one. And then after we understand all this, we then apply a software process design framework. Designing a software process for a project, product, or enterprise requires a fundamental understanding of what processes are made up of and best practices in processes. Once again, we will try to provide a framework consisting of principles and practices and a set of design criteria. As Charlie Brown says, OG, not another framework. First, let's look at process phases, a high-level categorization of process components organized by common intent. Once again, phases are process steps grouped by their common intent. Phases are termed requirements identification, analysis, architecture and design, implementation, testing, deployment, maintenance, and project management. These phases, the intents of these phases are, for example, understanding the domain and its problem, understanding what is to be developed and why, designing the system, developing the system, and then deploying, testing, and maintaining it. Incidentally, also as this process is unfolding, managing all of it is also a phase. Requirements is the phase where you identify the problem to be solved, detail the features of the solution, identify the business case and the acceptance criteria of the software. Essentially, requirements are those concerns of the system that its external stakeholders, such as customers and sponsors, are interested in. Analysis is essentially understanding. This understanding has to be at multiple levels, at the domain level, at the problem level, and at the solution level. Architecture and design taken together make up the phase where you determine the overall structure or architecture of the system and the design, which is what the individual components of the system are and how they work together. Architecture may be thought of as consisting of the design elements that once put in place are hard to change. You might also think of architecture as design decisions that have global impact, such as the programming framework, Enterprise Java, .NET, choice of database, and so on. Design is, well, design. You've seen that in whatever program that you wrote. The implementation phase is the phase where you actually build the system. Testing is the phase where you check if the system actually works, and if it doesn't work, where it doesn't work. Deployment is the phase where you actually take the steps to put the system to work. Deployment is especially complex in enterprise systems. Think of the insane spaghetti diagram in Lecture 1 and imagine inserting a new system in that mess. Maintenance is the phase where you keep the system working and keep it useful as needs evolve. I think sometimes that that's the phase that my wife thinks I'm in. Project management is the phase where you plan, organize, resource, lead, control, and coordinate the project. Project management consists of the steps needed in the overall monitoring and control of the process. Note that software lifecycle phases are groupings of activities clustered around a common intent. Phases are not steps done in the order shown. So if phases aren't ordered, what determines the process order? Software engineering steps are ordered in time by what are termed stages. Only in the waterfall model is the system supposed to progress steadily from requirements to design to implementation. In reality, software development is very complex, with a multitude of concerns to address, with surprises at every turn. Thus, software development cannot progress smoothly in a top-down manner. In fact, software development progresses in stages, starting from situations of little understanding to situations of progressively increased knowledge and predictability, starting from understanding the needs from the sponsors or the visionaries to involving the development team to releases to the customer. So let us now look at how a software project progresses that is, its stages. There are 4 stages: inception, elaboration, construction, and transition. Once again, these stages progress from a situation of high-level understanding and low certainty to detailed understanding and high certainty, with interactions beginning mainly between the sponsors, stakeholders, and high-level technical personnel, to then progressing to the development team and then to the consumers of the system, that is, its customers. The project may cycle through these stages many times during its lifetime. Potentially, this may happen as much as once per release, and perhaps even once per iteration if the system is complex and not well understood. The inception stage is the stage where you create an approximate vision, a business scape, a high-level scope, and a high-level potential architecture and high-level estimates. This is the stage where things are being figured out: vision, business case, scope, potential architecture, and high-level estimates of effort and cost. The elaboration stage is the stage where you refine the vision, validate the core architecture, resolve high risks, do most of the requirements identification, and create more realistic estimates. Elaboration is all about the resolution of the high risks: vision risks, business case risks, requirement risk, architecture risks. The core architecture, that is, the elements in your system that have to work, will be implemented here. At the end of this stage, you will pretty much know how much it will cost and how it will work, and you can then proceed after this stage to the more systematic cookie-cutter tasks. The construction stage is where you iteratively implement any remaining features and prepare for deployment. Essentially, the construction stage is where the tasks are steadily adding more and more features. The transition stage is the stage where you deploy a finished release. Here, the software is turned over to the customer or the users. Incidentally, you might also think of beta testing as a transition stage. While every project will go, perhaps more than once, through the 4 stages described earlier, the progression through the stages is very much project dependent. So what are some of the things that might affect the progress of a project from start to finish? The first characteristic is system size and its accompanying characteristic, system complexity. Then there are personnel issues: size of the team, composition of the team, culture of the team, proximity of the team, which is how co-located the team is, the uniformity of the team, which is how uniform in terms of skills the team is, and the stability of the team. In other words, what the turnover is in the team. Are people coming and going, or is the team pretty much constant in terms of people throughout the lifetime of the project? Thirdly, the clarity and dynamism of the goals or the requirements can affect the progression. In other words, a project may be exploratory and hence its requirements may be emergent. That is, in the project, people are trying things in order to figure out what the real requirements are. Such a project will spend a lot of time in the elaboration stage, whereas a project that is very well defined will progress quickly through to construction. Another factor is criticality of purpose. Saving or impacting lives is the mark of a critical project. The next level of criticality might be profit orientation. In other words, the company's business depends upon the project, or the goal of the project might simply be entertainment. A mission critical or life critical project will spend a lot of time in inception and elaboration because the team will want to make sure that they've gotten things right before they actually try to build it. Certainly, stakeholder expectations, such as the expected cost or the allowable cost and the allowable schedule, will affect the progression. Incidentally, note that there is no mention of technology here. Can you think why this is the case? Are technology issues not important? Are they already captured in the other considerations? Think about this, and if you have any questions, ask. And now to some best practices or good principles to follow in software development processes. Since a software system is complex, we typically try to reduce the complexity of development by attacking it in chunks. Incremental, iterative, and scenario-driven all mean essentially a divide and conquer approach. However, there are differences among these terms. Incremental simply means develop a system in pieces. Iterative means develop a system in pieces, but also for each piece, revisit any concern in each increment. In other words, you can include requirements all the way through to implementation, testing, and maintenance in each increment. Scenario-driven means that in each iteration, a user-visible piece of behavior is released. Thus, iterative is a subclass or refinement of incremental, and scenario-driven is a refinement of iterative. Software processes have to be comprehensive in that they must address the complete range of isolatable issues or separable concerns that influence the creation or the composition of the software system. We'll list many of these separable concerns below, categorized by the phases. Verify for yourself that each of the concerns here are indeed separate, although of course they may influence each other. This slide lists the important requirements and analysis concerns. With respect to requirements, the separable concerns are the problem that is being solved, which is the why from a functional point of view, the business case for the project, which is the why of the system from the business point of view, the user perspectives, basically how the user will see the system and interact with it, the visible function, which is what the system is supposed to do, the non-functional requirements, which is how the system is supposed to do it, prioritized requirements, which is what is the relative importance of all these requirements, and finally the acceptance criteria, which is how the customer is going to validate the system. With respect to analysis, the separable concerns are the static structure of the problem or the system, the dynamic behavior of the problem or the system being built. Note that analysis is done at multiple levels, at least at 3 levels: domain analysis, problem analysis, and solution analysis. Depending upon the extent to which that you do each of these analyses is dependent upon the complexity of the problem. This slide lists the important architecture and design concerns as follows. The system architecture, the high-level view of how the system meets or could meet the functional and non-functional requirements. The target environment, a view of the system architecture that shows what platforms the system will be deployed on. The subsystem model, which is a view of the system architecture that shows the partitioning of the system into smaller systems. The detailed static structure of the system components. The detailed dynamic behavior of the system components. Note that there are high-level so-called architectural concerns and high-level so-called design concerns. Note also the need to address both static and dynamic concerns. With respect to project management, the concerns are the design of the overall process, the availability and composition of the resources, human as well as technological, the delivery schedule, the partitioning of the system development into releases and iterations, and the addressing of risks. In implementation and testing, the concerns are the management of code, and specifically with respect to testing, unit level, component level, and system level validation. The next 3 considerations or concerns span phases. They cannot be categorized or they are not specific to any phase. These 3 considerations are A, verification, which is doing the thing right, validation, which is doing the right thing, and then traceability, which can be both forward and backward. Verification is all about whether something was created by following the prescribed actions in the right way. Validation cares about whether what you built or did was the right thing to do. So for example, if a doctor were injecting a drug, verification is all about whether the needle was sterilized, that the patient was anesthetized, the doctor washed his hands, etc. Validation, on the other hand, is whether the patient had a better medical outcome, that is, the patient was cured or at least wasn't killed because of the drug. Traceability is the notion that the actions taken to address these separable concerns are actually need to be interrelated or tracked in a way that is verifiable. So for example, if you captured requirements, you should be able to trace each requirement to the code that implements it, and vice versa, which is you should be able to trace back from any code segment to the requirement that the code implements. Traceability is thus both forward from an upstream concern to a downstream concern, and backward, which is the reverse. Next, we present a set of principles for good process design. These principles include communication and visibility, providing feedback as quickly as possible after each completed task, for example, by unit testing every component before it's checked in, and keeping inventory small, such as not having a lot of untested stuff lying around or a bunch of unimplemented requirements scoped in, and so on. There are also people principles, showing respect for everybody's opinion, showing courage in development, such as speaking up, ruthlessly testing code, taking on new tasks, and so on. The point here is that processes are executed by people, and we've got to keep people considerations in mind as well. And the last principle is the principle of sustainable work, which is the principle of not overloading a team, and also by keeping a constant velocity in the project, rather than running the project in a way that there are large swings in the amount of effort put in by the people doing the project from day to day. And lastly, there is the principle of using risk to drive the management of the project. Note that there are two kinds of risks. The first kind of risks are about system expectations, which is things like functional and non-functional requirements. These risks are met by the software development process. But also there are orthogonal, or what we call project risks. These are handled by risk planning. Risk planning will be something that will be covered in a later lecture. So if processes have to be designed differently for each project or environment, based on these best practices and principles, how do we go about doing this? The next set of slides talk about customizing processes. Let's start by looking at where processes can be customized. They can be customized at these following points, if you will. What values are prioritized can be customized. For example, do you value sustainable constant speed as opposed to the meeting of schedules? There might be good reasons for picking one over the other. Do you seek to control visibility instead of making everything open? There's often a good reason for managing visibility. Think Apple or a military organization working with a civilian subcontractor. There are things that the military organization has that the civilian subcontractor must not see. The philosophy of management, whether the philosophy is going to be monitoring and adjustment, or whether it's going to be around planning and prediction, whether the philosophy is going to be around consistency, or whether it's going to be around accuracy, whether the management is going to use relative estimation versus exact prediction of effort and cost. You'll see examples of these in later lectures. Another place where the process can be customized is which separable concerns need to be managed tacitly or kept in people's heads and understood as sort of the memory and the social fabric of the team, and which should be managed explicitly, that is, put down in documents. This decision will lead to the identification of work products, that is, the documents used to keep track of the system. The next customization point is in the defined roles. And this is connected with the previous point in that the roles that you specify are determined by the degree of tacit versus assigned knowledge as well as accountability. You can decide upon the release and iteration structure. So for example, you can have releases that could have varying time and iterations that could have varying time depending on what you want to accomplish in that release or iteration. Or the release or iteration might be time box. That is, we release whatever we have that is validated every 3 months, or every iteration will last 3 weeks, things like that. You can customize the degree of co-location and communication required for the project, whether people are allowed to work from home, whether you are going to have a developer that is remote in some other city or country, things like that. And finally, you can also customize the specific techniques you use to deal with each concern. So for example, you might use use cases for capturing the user perspective of a system. You might use UML as a notation. You might use code reviews and test coverage analysis in your testing or code management, things like that. Typically, after you've done all the customizations, you will end up with a process whose parts each conform to a certain style. This style may be broadly categorized as structured or agile. That is, you can look at each piece of the process or each part of the process and say, yeah, this piece is structured in style and this other piece follows the agile style. So how do you begin customization? You follow the following steps. Step 1, break the system into logical components as per its architecture. Step 2, evaluate the risk for each component as follows. Apply the spider diagram on the right by marking where your project falls in each of the categories shown. Next, pick the style of process that addresses the risk best. That is, if the points on the axis fall close to the center, then the style should be agile. If the points on the axis are close to the outside edges, the style should be structured. Note that the idea is that each partition, each component is done in a purely agile or purely structured manner. However, your analysis might show neither a compact circle nor around the origin, nor a well spread out web near the edges. In such cases, you have to carefully examine the risks for the component. There are basically three kinds of risks. Environmental risk that results from the project's general environment that applies to both kinds of processes as follows. The technology to be used has many uncertainties. Many diverse stakeholders need to be coordinated. The system is not small, it's a complex system of systems. Think about what process you might use for these three things. So for example, if the technology to be used has many uncertainties, you'd probably use an agile approach to validate the technology. If many diverse stakeholders need to be coordinated, you might want to use a structured or plan-driven approach to do all the coordination. And if it's a complex system, then you probably don't want to approach it in an agile way if the system is mission critical. Of course, if the system is for entertainment or for not something that has high business or life or death implications, then you could do a complex system in an agile way as well. Then there are agile risks that are really risks that are specific to the use of agile methods. So for example, if scalability needs and criticality are high, or if simple design might not work, or if there are not enough people skilled in agile methods, doing a project a component in a system in an agile manner will be risky. Similarly, there are structured risks as well, risks that are specific to the use of structured methods. So for example, if there is rapid change in the requirements, long-term planning will be useless, in which case a structured approach won't work. If there's a need for rapid results because schedules might be tight or the customer needs to show something to a sponsor before getting funding for the whole project, things like that, then a structured process will work less well. If there are emergent requirements, that is requirements that emerge after you try something out, then a structured process doesn't work well. And similarly, and just like with Agile, if there are not enough people skilled in plan-driven methods, things like creating project plans, drawing detailed UML diagrams, and so on, that's a risk for a process that you would like to drive in a structured manner. Once you have analyzed these risks, if the predominant number of risks fall under Agile risks, then you need to pick a structured process. And if a lot of the risks fall under the risk for structured processes, then you have to pick an Agile process. So finally, we are reaching the end of the lecture. So here's where we summarize what we have tried to convey to you and what we expect you to have learned. First, the benefits of software engineering processes, or rather, firstly, the concepts behind software engineering processes, and the benefits of software engineering processes. Secondly, some understanding of the principles and best practices behind software engineering practices. Things like the actual techniques used, which by the way we will be covering in the later lectures. This notion of separation of concerns, verification and validation, traceability, the people principles, and the risk-driven focus. And the last learning outcome of this class was around design, so which was all about identifying customization points, doing project partitioning, doing agile versus structured analysis, this idea that each partition should be done purely agile or in a purely structured manner. Here's a list of references and additional reading material for this lecture. The first reference is a book from the IBM Object-Oriented Technology Center called Developing Object-Oriented Software, an Experience-Based Approach. The chapters of this book have been posted online for you to access electronically. In this book, chapters 1, 2, 3, and 4 are required, and chapters 5, 6, and 7 will be needed for the project. By the way, additional chapters as well in the lectures that follow. And the second reference are extracts from a book called Balancing Agility and Discipline. Extracts from this book have also been placed online, and this reading is also required.